Lecture 21 covers sections 6.7 through 6.8. At the end of today's lecture, you should be able to evaluate the relation between pressure, temperature, specific volume, and K for ideal gases undergoing an isentropic process. For us to quantify our change of entropy for ideal gases, i.e. that is, how our ideal gases behave undergoing an isentropic process, let us recall Gibbs's equations. Gibbs' first equation for an ideal gas can be expressed as our change of entropy is equal to our constant volume specific heat times the natural log of T2 per T1 plus R times the natural log of nu2 per nu1. Gibbs' second equation can be expressed as our change of specific entropy is equal to our constant pressure specific heat times the natural log of T2 per T1 minus R times the natural log of P2 per P1. For isentropic processes, ds is equal to 0. When an ideal gas undergoes a reversible process, we have then 0 is equal to Cp naught times the natural log of T2 per T1 minus R times the natural log of P2 per P1. If we rearrange this in terms of temperatures, we have the natural log of T2 per T1 is equal to R per Cp naught times the natural log of P2 per P1. If we exponentiate to solve for a ratio of temperatures, we have T2 per T1 is equal to P2 per P1 to the R per Cp naught. Now, if we recall R, our gas constant, is equal to our constant pressure specific heat minus our constant volume specific heat, our exponent, R per Cp naught, can be expressed as Cp naught minus Cv naught per Cp naught. And if we define K as the ratio to our constant pressure to constant volume specific heats, this can be expressed as K minus 1 per K. And K is defined on table A5. Thus, for an ideal gas undergoing an isentropic process, T2 per T1 is equal to P2 per P1, this quantity, to the K minus 1 per K. We will call this equation 1. The pressure of an ideal gas, P, can be expressed as our gas constant times our temperature per our specific volume. If we substitute this expression into the right-hand side of equation 1, we'd have P2 per P1, the quantity to the K minus 1 per K, is equal to the quantity R T2 per nu2 times the quantity nu1 per RT1, this quantity to the K minus 1 per K. Since R is constant, we'd have T2 per T1 times nu1 per nu2, this quantity to the K minus 1 per K. If we recall equation 1, that the left-hand side, T2 per T1, was equal to the right-hand side, P2 per P1, to the K minus 1 per K, we can re-express the left-hand side of our previous equation in terms of temperature. That is, T2 per T1 would be equal to T2 per T1 to the K minus 1 per K times nu1 per nu2 to the K minus 1 per K. Or we'd have T2 per T1 to the 1 per K is equal to nu1 per nu2 to K minus 1 per K. Now if we exponentiate both sides to K, we'd have T2 per T1 would be equal to nu1 per nu2 to the K minus 1. Thus we have a relation between temperature and specific volume between our initial and final states. Lastly, if we express the ideal gas law in terms of temperature, where T is equal to our pressure times our specific volume per our gas constant, and we substitute this into the left-hand side of equation 1, we'd have P2 nu2 per R times R per P1 nu1 would be equal to P2 per P1 to the K minus 1 per K. If we group like terms, we'd have nu2 per nu1 would be equal to P2 per P1 to the minus 1 per K. Now if we rearrange in terms of pressure and exponentiate to minus K, we'd have P2 per P1 is equal to nu2 per nu1 to the minus K. Alternatively, we could express this as P2 per P1 would be equal to nu1 per nu2 to the K. Thus we have a relation between pressure and our specific volume. It is evident from equation 3, i.e. P2 per P1, which was equal to nu1 per nu2 to the K, which could be expressed as P2 nu2 to the K, being equal to P1 nu1 to the K, that this is a familiar formulation. That is, P nu to the K is a constant, i.e. this has the same form as a polytropic process. Now if we express the change of entropy for an ideal gas undergoing an isentropic process, our pressure times our specific volume between our initial and final states must remain constant. And this constant of proportionality can be considered our polytropic index. That is, we can define N now as K. Now, if our process is isentropic, we are going to use K, our ratio for constant pressure to constant volume specific heats, taken from table A5, which we defined previously as gamma, which was defined for an isentropic process. If it is not an isentropic process, we simply use N. Now, since N is equal to K, i.e. we substitute our polytropic index for K for an ideal gas undergoing an isentropic process, we can express our previous formulations in terms of our polytropic index. That is, we have a relation between our pressure and volume, that is P2 per P1, would be equal to nu1 per nu2 to the n. We'd have a relation between temperature and pressure, that is T2 per T1 would be equal to P2 per P1 to the quantity n minus 1 per n. And then we'd have a relation between temperature and volume, that is T2 per T1 would be equal to nu1 per nu2 to the power n minus 1. Now this allows us to evaluate various forms of work for an ideal gas. Now if we have non-isothermal work going from state 1 to state 2 would be P2 V2 minus P1 V1 per 1 minus n. Now if we express P and V in terms of the ideal gas law, the work for a reversible polytropic process, work going from state 1 to state 2, would be equal to m times r times the difference of temperatures between state 2 and state 1 per 1 minus n. Now, if this process is an isentropic, n would be equal to k. If this process was not isentropic, we would just use n. Recall for an isothermal process, our polytropic index was equal to unity, and thus the evaluation of work was executed through the integration of the change of our volume. That is, work from state 1 to state 2 is equal to integral from state 1 to state 2 of PdV, which would be equal to P1 V1 times the integral from state 1 to state 2 of 1 per V dV, which was equal to P1 V1 times the natural log of V2 per V1. If we re-express state 1 in terms of the ideal gas law, recalling that our temperature is the same, and the ratio of volumes in terms of pressure, the work for a reversible isothermal process would be work going from state 1 to 2 being equal to mass times our gas constant times our temperature times the natural log of P1 per P2. Lastly, if we wanted to quantify the amount of heat transferred through this isothermal process, we have to recall that U and H are dependent only upon temperature, and therefore in an isothermal process, there is no change of our internal energy, and heat must be identically equal to work. Our heat added is simply our temperature times our change of entropy, where delta Q is equal to TdS. Therefore, for isothermal heat transfer, Q going from state 1 to state 2 is equal to our work going from state 1 to state 2, which is equal to our temperature times our entropy at state 2, less that at state 1, which is equal to a mass times our gas constant R times our temperature times the natural log of P1 per P2.